All the halides which are formed by alkaline earth metals, they are ionic in nature, but the beryllium halides are covalent in nature and they will soluble only in organic solvents. Magnesium nitrate crystallizes with 6 molecules of water. How it will be formed? The nitrates are made when dissolving carbonates in dilute nitric acid. When calcium oxide is treated with water, it will form calcium hydroxide. That will be called as slaked lime. How it will be formed? By this reaction. Hello everyone, this is Harshita Bhavasar from Vidhyaashram School of Excellence. Today we are starting up session 4 from the chapter S block elements. In the last session, we have discussed group 2 elements, that is alkaline earth metals, its properties like ionization enthalpies, hydration enthalpy, physical properties and some of the chemical properties we have discussed. In this session, general characteristics of compounds of alkaline earth metals, oxides and hydroxides and some of the halides. General characteristics of compounds of the alkaline earth metals. Alkaline earth metal ions are uniformly dipositive in their compounds. Due to increased nuclear charge and smaller size, the alkaline earth metals form ionic compounds which are less ionic than corresponding compounds of the alkali metals. Alkaline earth metals, we know that it is having dipositive ions, means M2+. Due to increased nuclear charge and smaller size, it will form ionic compounds. The oxides and salts of light and small sized members such as beryllium and magnesium are more covalent than those formed by the heavier and larger sized members like calcium, strontium, barium. Only like oxides and salts of light and smaller sized beryllium and magnesium elements, they will form covalent compounds, but other like calcium, strontium and barium will form ionic compounds. Next, oxides and hydroxides. All alkaline earth metals form oxides of the formula MO except beryllium oxide which has rock salt structure. All the alkaline earth metal will form oxides like metal oxide like MO, but the beryllium will not form any oxide because it will form rock salt structure. The bond in beryllium oxide is essentially covalent. The enthalpies of formation of these oxides are quite high and consequently they are very stable. The beryllium oxide will form whatever it is forming, it is covalent in nature, not in ionic, and also the enthalpy of these oxides are quite high and it is very stable. Beryllium oxide is amphoteric in nature, both acidic and basic in nature. Metal oxide, beryllium oxide 550, that is enthalpy of formation. This is magnesium oxide, calcium oxide, strontium oxide and barium oxides. It is 550 in nature, this is 590, this is 623, again it is 590 and 545. The solubility, thermal stability and the basic character of these hydroxides increase with increasing atomic number from magnesium hydroxide to barium hydroxide. The solubility, product or the thermal stability and the basic character of these hydroxides increase with the increasing atomic number, that is from magnesium to barium hydroxide. Beryllium hydroxide like BeO reacts with acids and alkalis forming amphoteric products. Beryllium hydroxide, in the sense beryllium oxide, reacts with acids and bases to form amphoteric products. See here, beryllium hydroxide plus base means beryllium hydroxide, that is berylliate ion. Beryllium hydroxide with acid and water means beryllium hydroxide, that is with chlorine it will form. Next, halides. All alkaline earth metal halides except beryllium halides are ionic in nature. Beryllium halides are covalent and are soluble in organic solvents. All the halides which are formed by alkaline earth metals, they are ionic in nature, but the beryllium halides are covalent in nature and they will soluble only in organic solvents. The beryllium halide molecules exist only in gas phase, but in the condensed phase it consists as a polymer as shown below. Usually it will be present in gas phase or gas state, but in the condensed state it will be act as polymer. Okay, this is beryllium, this is halogen, and it will be formed like a polymer. See, BEX, again BEX, again BEX. It will be like polymer. Okay. Of the other halides, only magnesium bromide and magnesium iodide are soluble in organic solvents. The tendency to form halide hydrates gradually decreases down the group. Except magnesium bromide and magnesium iodide, all will dissolve in water itself, but with magnesium bromide and magnesium iodide, it will also dissolve in not polar organic solvents. And the tendency to form halide hydrates, whatever the metals are forming halides, and with halide hydrates, down the group the tendency will keep on decreasing. The hydrated chlorides, bromides and iodides of calcium, strontium and barium can be dehydrated by heating, but those of magnesium and beryllium suffer hydrolysis. The fluorides of alkaline earth metals are sparingly soluble in water, and the solubility increases slightly with increase in cation size. Means the fluorides of alkaline earth metals are sparingly soluble in water. Sparingly means not completely or not partially also, and the solubility increases slightly with increase in cation size. As the cation size increases, the solubility will also increases. Calcium fluoride is the only large scale source of fluorine. Next one, salts of oxo acids. First, carbonates. Most of the beryllium salts of strong oxo acids can be crystallized as soluble hydrates. By solubling or by dissolving hydrates, the beryllium salts of strong oxo acids can be crystallized. Beryllium carbonate is prone to hydrolysis and can be precipitated only in an atmosphere of carbon dioxide. How it will be hydrolyzed? By using atmospheric carbon dioxide. The carbonates of magnesium and other alkaline earth metals are sparingly soluble in water, and their thermal stability increases with increasing cationic size. What they are telling, magnesium and other alkaline earth metals will also form carbonates. Those carbonates will sparingly soluble in water. It is also not partially or not completely, and their thermal stability increasing in cation size. All these carbonates are more soluble in the presence of carbon dioxide in water owing to the formation of hydrogen carbonate ion, but bicarbonates have not been isolated in pure state. When it will be completely dissolved or soluble in water means there should be atmospheric carbon dioxide surrounding it. That time the formation of hydrogen carbonate ion can be formed with bicarbonates in the isolated pure state. Calcium carbonate finds use in solvase processes for the manufacture of sodium carbonate in glass making and cement manufacture. How the calcium carbonate will be used in solvay process? They have used not only in solvay process, in glass making and in cement manufacturing also calcium carbonate will be used. Next, sulfates. The sulfates of alkaline earth metals are white solids and stable to heat. Okay, they are white solid and they are non-reactive to flame or heat. The sulfates like beryllium sulfate and magnesium sulfate are readily soluble in water. The solubility decreases from calcium to barium. Beryllium sulfate and magnesium sulfate are soluble in water and decreases from calcium sulfate to barium sulfate. Beryllium, magnesium and calcium sulfates crystallizes in hydrated form. How it will be present in hydrated form? In these three sulfates will form crystalline in the hydrated form, not only separated. See here, beryllium sulfate, tetrahydrate, this is magnesium sulfate, heptahydrate, this is calcium sulfate, dihydrate. The sulfates of strontium and barium crystallizes with water. The greater hydration energies of beryllium and magnesium ions overcome the lattice energy factor and therefore their sulfates are soluble. The sulfates of strontium and barium crystallizes with water. means it will crystallize with water and it will overcome the lattice enthalpy of it and it will form more hydration enthalpy. Next, nitrates. The nitrates are made by dissolving carbonates in dilute nitric acid. Magnesium nitrate crystallizes with 6 molecules of water. How it will be formed? The nitrates are made when dissolving carbonates in dilute nitric acid. Carbonate should be dissolved in dilute nitric acid, then the nitrates will form. In that example, magnesium nitrate crystallizes with 6 molecules of water. Barium nitrate crystallizes as the anhydrous salt. All of them decomposes on heating, giving the oxides. It will decompose and it will form oxides. Strontium and barium nitrates are used in pyrotechnics for getting red and green flames. In the salt analysis, we have seen that when salt has been taken in the watch class and it has been mixed with acid and it will be projected to flame, means it will give or it will impart some of the colors, like strontium give red, gentle red, and barium nitrate will give green flames, right? That is what they are explaining. Next, anomalous behavior of beryllium. In the alkali metals, we have seen anomalous properties of lithium like that. Here also some of the properties are not like same as to alkaline earth metals of beryllium. So we are reading these properties. The properties of beryllium, the first member of the alkaline earth metal, differ from rest of the members. It is mainly because its small size and high polarizing power, relatively high electronegativity and ionization energy as compared to the other members, absence of vacant d orbitals in its valence shell. Why beryllium is having anomalous property and why it is not similar to the rest of the alkaline earth metal members means it is having small size because it is the first member of alkaline earth metal. It is having high polarizing power and it is have high electronegativity also and ionization energy also, and it does not have vacant d orbitals in its shell. Next, some important points of difference between beryllium and other members, especially magnesium, are given below. Beryllium is harder than other members of its group. Beryllium is lighter than magnesium. They are comparing with beryllium and magnesium. Beryllium is harder. Beryllium is lighter than magnesium. It is harder but lighter than magnesium. Its melting point and boiling points are higher than those of magnesium and other members. Beryllium does not react with water while magnesium reacts with boiling water. Beryllium oxide is amphoteric while magnesium oxide is weakly basic. Beryllium forms covalent compounds whereas other members form ionic compounds. Beryllium carbide reacts with water to give methane whereas carbides of other alkaline metals to give acetylene gas. This is the different point and these are all points we have discussed in the other concepts deeply and with the exceptional case with beryllium. This only extra point, beryllium carbide reacts with water to give methane whereas carbides of other alkaline metals gives acetylene gas. Okay, other points we have seen with explanation. See, beryllium carbide with water, beryllium hydroxide and methane will form, and magnesium carbide with water will form magnesium hydroxide C2H2 ethene, and calcium carbide will form react with water, calcium hydroxide and ethane will form. Next point, beryllium does not exhibit coordination number more than 4 as it has 4 orbitals in the valence shell. The other members of this group have coordination number 6. About coordination chemistry you will study in the second year. There you will understand about coordination number and the overall chemistry of coordination. Here the beryllium will not form more than 4 coordination number because it does not have more than 4 shell, but other alkaline earth metals will form 6 coordination number. This is extra or another anomalous property of beryllium. Next, diagonal relationship between beryllium and aluminium. How it will be? Beryllium and aluminium will be diagonally have a relationship. Okay. Beryllium is present in the second group, aluminium is present in the 13th group. Though it is having the diagonal relationship. How it will be? Let's see now. Due to the same charge or radius ratio between beryllium and aluminium, They show many similarities between them. Some of the similarities are both aluminium and beryllium form covalent compounds. We know that other alkaline earth metals will form ionic compounds, but beryllium will form covalent compounds like aluminium. The hydroxides of beryllium like beryllium hydroxide and aluminium hydroxide are amphoteric in nature, means it acts as both acidic and basic nature. The oxides of both beryllium and aluminium are high melting insoluble solids. It doesn't get melt very easily. Beryllium chloride and aluminium chloride have bridge chloride polymeric structure. See here, beryllium chloride will also have bridge structure and aluminium chloride will also have polymeric bridge structure. Next, the salts of beryllium as well as aluminium are extensively hydrolyzed. This can be extensively hydrolyzed. Carbides of both the metals react with water, liberating methane gas. See here, beryllium carbide when reacts with water, it will also form methane. When aluminium carbide reacts with water, it will also form methane. This is the one more similarity. The oxides and hydroxides of both beryllium and aluminium are amphoteric and dissolve in sodium hydroxide as well as hydrochloric acid. Okay, the oxides and the hydroxides of beryllium and aluminium are amphoteric and dissolve in sodium hydroxide as well as in hydrochloric acid. This beryllium oxide dissolve in 2HCl, that is hydrochloric acid, it will form beryllium chloride. When beryllium oxide reacts with sodium hydroxide, it will form sodium beryllium oxide. Aluminium oxide also react with hydrochloric acid, will form aluminium chloride. When aluminium oxide reacts with sodium hydroxide, it will also form sodium aluminium oxide with the liberation of water. The reactions are same. Like aluminium, beryllium is not readily attacked by acids because of the presence of an oxide film. Usually for aluminium, the acid cannot attack due to the oxide film is present. Like that, beryllium also cannot be attacked by acid. These are the similarities between beryllium and aluminium. Next, important compounds of calcium. First one, quicklime, that is calcium oxide. How it will be prepared? It is prepared on a commercial scale by heating limestone, that is calcium carbonate, in a rotary kiln at 1070 to 1270 Kelvin. Calcium carbonate, it has been heated means or decomposed, it will form calcium oxide with carbon dioxide. There is a reversible reaction, it is endothermic in the forward direction to ensure that the limestone is completely converted to lime. Carbon dioxide is allowed to escape from the kiln. This makes carbon dioxide unavailable for the reverse reaction. It is a reversible reaction and it can be converted to calcium carbonate also. Lime is a white amorphous solid. There are two types of solid, crystalline and amorphous. We know that amorphous is like completely talcum powder like property. It has a high melting point of 2600 Celsius. It is highly stable and even fusion cannot decompose it. Chemical properties: on adding water, quicklime forms slaked lime or lime water. When water is added to lime, it becomes hot and cracks to form a white powder. This is called slaking of lime. See here, when calcium oxide is treated with water, it will form calcium hydroxide. That will be called as slaked lime. How it will be formed? By this reaction. Quicklime absorbs carbon dioxide to form calcium carbonate. When the calcium oxide reacts with carbon dioxide, it will form calcium carbonate. Its uses, calcium oxide uses is, lime is indispensable for use with mortar and pestle plaster. It is used as a laboratory reagent for gas absorption, precipitation, dehydration, etc. It finds enormous use in the manufacture of soap, rubber, varnish, refractories and lime bricks. It also finds use in the preparation of calcium carbide, basic calcium nitrate and calcium bisulfate. To form these compounds, the calcium oxide will be used. It is an important primary material for manufacturing cement and is the cheapest form of alkali. It is used in the manufacture of sodium carbonate from caustic soda. It will be used in the manufacture of sodium carbonate. It is employed in the purification of sugar and in the manufacture of dye stuffs. When the sugar has been prepared, it will be treated with this calcium, okay, and for the purification of sugar. This is about the uses of lime. In the next session, we will discuss about calcium hydroxide, calcium carbonate, plaster of Paris, cement, and biological role of magnesium and calcium. I hope you have understood completely whatever I have taught today. We'll meet in the next session. Thank you.